Hi, my name is Xiaoming Li, and this is the demonstration for the computer visualization of the billiard problem. The billiard problem is studied in analytic number theory, and there is a paper by Professor Florin Boca and Professor Alexandru Zaharescu. They have studied the average length of the trajectory of the tiny ball or tiny particle running on the square billiard table. So imagine you have a square here and you have four pockets on the corners, and you shoot a particle from some location on the table. Let's say if you shoot from the middle of this side with angle 45 degrees, then you can imagine it's going to loop forever. However, in the paper, the problem setting is you shoot the particle from one of the corners. Let's say this pocket. You shoot from this pocket with some angle theta. Then you can imagine it's going to bounce back and forth when it meets the boundary. So to study the length, we can actually convert this problem into several different kinds of problems which are easy to study. And I found it very interesting, so I have decided to do the visualization of this problem. So here we have some variables. Theta is the angle you shoot. So like if you shoot from the along this direction, then it's going to be 45 degrees, and you convert it to radius. So it's pi over 4. And epsilon here, the second variable epsilon, is the pocket size. So it's just the radius of this circle here. And speed is for the user to adjust the speed of drawing the trajectory. I have provided two modes to draw the trajectory. The first one is you can input the theta by either inputting the value, like typing the value here, or you can just drag the slider to change the value of theta. Let's just try this mode first. After you have decided your angle theta, then you can just click the button shoot. You can see the trajectory length is displayed on the screen and is changing dynamically when you're drawing the trajectory. So what are the other pictures here? What are those two other tables here? Let's just look at the first one, this bigger one. So to study the trajectory length, you can imagine if the particle does not bounce back when it meets the boundary, what if it can pass through? You can just flip this board to get a mirrored image, a mirror board next to it. And in this sense, you're kind of like unfolding the trajectory to make it become straight, become a line segment. You repeat this process, then you get what's on this table. So each square corresponding to here. And this one next to it is just the flipped one, the mirrored image of that. And you repeat this process. So if you say this side has unit 1, the length is 1, then here you can see all the pockets, they're just lying on the lattice points. So you have got another board on R2, and to study this trajectory length is the same thing as studying some ray shooting from the origin with angle theta. You can just look at what's the first lattice point this ray is gonna meet. That's the destination of this line segment, and the length of this line segment is the same as the length of the trajectory on the unit board. And I've colored four sides of the board with different colors. And if you look at the images on this on R2, then you can see what's repeating is not the unit square. It's the 2 by 2 block. And the reason is you flip anything twice, you get the same thing. So what's repeating is this 2 by 2 block. And that's also the reason I have drawn this 2 by 2 block here. You can also imagine the trajectory is going to be parallel lines on this 2 by 2 block. It's going to shoot from here and going, when it meets the boundary of this block, then it just goes back to the other side at the same location, the same y coordinates, and continue. So this is it's pretty much like the video game Snake. You meet the boundary and then you disappear, you reappear on the other side with the same kind of location. Here is y coordinates the same. Sometimes it can be the x coordinates. So that's another interesting thing. And you have a block here. what you can also do is you can glue the opposite sides of this block, this bigger square. So you glue the blue sides and glue the purple sides. What you get is a torus. It's corresponding to this torus on the right side. So how many pockets do we have? Let's count. There is one from the center, and there's another one from the four corners of this bigger block. And there are two more from these four pockets on the middle of each side. So you have four pockets in total on the torus. And I have drawn them using two different colors, two in orange and two in blue. So you have two outer pockets and two inner pockets. So before I demonstrate some functionality related to the torus, let's try the second mode first. So let's just adjust the epsilon a little bit, and it's not hard to see if you have a bigger size epsilon, then it's just easier for the pockets to capture the particle. So let's adjust the speed a little bit. If you have chosen this mode, then the dashed line is changing along the location of your mouse cursor. So you can use this to decide the angle theta. Let's say you want to shoot from here. After you decide, you can just click. And it's going to start drawing the trajectory. So here on the torus, what we can see is you start from this orange outer pocket, and the only possible destination are the four pockets, two inner pockets, two outer pockets on the torus. Moreover, because what we're gluing is not the original unit square, what we're gluing is this four square block. So because as we mentioned, it's going to be parallel lines. After you glue that, because originally it's just disappear and appear at the same location, at the same coordinates. So after you glue that, they're just glued together. So you're not going to see like behavior of like bouncing back when it meets the boundary on the torus, because there's no boundary on the torus. It's going to be a continuous curve, as you have seen here. And one functionality I have added is it's going to always facing your mouse cursor. It's going to rotate along the location of your cursor. If you want to stop this, you can just click these checkbox. You have checked that, then it's going to stop. Then you can use the two sliders next to it to control the rotation of this torus. So this is actually a research project led by Professor George Francis. We have different group members, each doing their own project. And I have found this problem very interesting. I have learned it from a course of exponential sum by Professor Zaharescu, and that's why I have decided to do some visualization of it. So I have included the link to the website of Professor Francis, and it's gonna also include a PDF file. It's gonna be a file like this, which contains more mathematical background and like more instructions on how to use this web page to play with it. Yeah, so that's the end of our journey. Thank you.